I hope you're doing better than I did there this week. Yeah, it was an interesting. Yeah, I don't know. We didn't get COVID tested, but it might have been. It was basically 48 hours of chills, and it's communicable because still trying to figure out if my daughter brought it home or I gave it to her or my wife got it too. So, but son was all right. But anyway, we seem to be back on track, and I hope everything's going all right. We're just gonna go through the week 9 PowerPoint. It's 3:17, so my Rugrats will be coming home anytime soon. So I'll probably start and stop this thing so a couple of times. So there might be a couple of videos. Just watch them in order. I'll label them in order, and I'll shoot you guys the links. And I'm telling you this because you're already watching it. So if you've already watching it, then let's just move on, shall we? Um, we're the since like week eight, since week 7, week 8, week 9, even week 10 is going to be solutions. And like last week there, I kind of introduced acids and bases. I'm going to come back to it there, the second half of the PowerPoint. And we're going to come back to acids and bases there next week when we are dealing with equilibrium. Uh, but we'll get into the acids and bases there in a bit. Just want to backtrack a little bit and go back into solutions because I think water itself is an amazing aspect, and some of the things here that I'm going to show you or introduce you to, you guys should pretty much know most of this stuff anyway. But some of this stuff we're going to come back to there in about 2 or 3 weeks. So a lot of this is going to be foreshadowing. Let's go. Let's go. Let's go. Vapor pressure. What we're talking about here is, and just look at the diagram here, we have one phase, like we're inside of a flask here, and there's your phase there, your liquid phase, then you have your gaseous phase. And you'll see there that evaporation, this is the molecules there that are moving from the liquid phase can escape to the vapor phase. So they see that they're moving in this direction. Okay, and there's that boundary, interphasal boundary. And you'll see there evaporation occurs. These molecules there, they just dissipate out. And you got to think there that depending upon the solution or whatever's in the flask here, if it's a water-based, the water, and we'll get into hydrogen bonding, water can act like, cement, right, with these hydrogen bonding and all that. So if it's a water-based there, it would be more difficult for evaporation. But if it's, look at volatile liquids here, we're talking about non-polar liquids. And being a non-polar liquid, these molecules really don't have any attraction to each other. Unlike water, where all parts of water are being attracted to all other parts of water, which is why water can be a tough, it can act like a solid, if you do a backflip off a diving board. Okay. But volatile liquids there, they really don't have any attraction to each other, so they will evaporate, okay, at a faster rate. Put the lid on, okay, and you'll see there that the evaporation will continue, but then because of the coolness there against the glass, it will condense and come back as water. All right, so just a couple words there: evaporation, condensation, nothing too crazy, okay? Vapor pressure. Dealing with vapor pressure, the whole idea here is that we are being bombarded by gazillions of molecules, okay, that are pushing on us. And it's just like if you think of, not to jump ahead a slide here, but I'm gonna, think of this as if you were here and this was the bottom of the ocean, you'd have 8 kilometers of water on top of you. That's why, we'd be the size of a Coca-Cola can at the bottom of the ocean because of the water pressure pushing down on us, right? It has a mass. And and the closer there we are, we're higher up, there would be less pressure. All right, same principle here. Air has a mass. It is a thing, so therefore it has mass. But you see here, like let's say here, this is at ocean level. Okay, let's say we've got 20 kilometers of air pushing down at us. It's not heavy enough for us to kill us, but it exerts a force, and a greater force than what's going on here at the top of Kilimanjaro or Mount Everest or wherever. And you'll see here that water boils at 100 degrees Celsius. Okay, boiling point, temperature at which the vapor pressure of a liquid is equal to the external pressure above the liquid. So here at ocean level, okay, we're at the beach and I'm boiling water at 100 degrees Celsius. Okay, now why does water boil at 100 degrees Celsius? Because it's at that temperature there that the temperature at which the vapor pressure of the liquid is equal to the pressure pushing down from the air. Okay, and so at 100 degrees here on the beach, water boils, but if you go to the top of Mount Everest, I think water boils in the 70 degrees area, whether it's 78 or 77, somewhere in there. You can Google that one. All right, and why? Because there's less vapor pressure. Okay. How do we measure pressure here? Here in SI countries like Canada, we measure pressure there in kilopascals, and a normal day, a nice sunny day, is 101.3 kPa, which is equivalent to 1 atmosphere, okay, scientifically speaking. And then if you're from America or Britain, a handful of other countries there that still use the old school imperial method there, which is called the torr, which is also millimeters of mercury. Okay, being able to flip in and out of those shouldn't be an issue. Okay, just using the certain ratio, I could ask you here, how many atmospheres are in 1,000 millimeters of mercury? Well, you set up the ratio right here. How many atmospheres are in 1,000 millimeters? So 1,000 here, cross multiply, you're kind of doing a box here, and you find your answer, and away you go. So these three numbers here are interchangeable, okay, and we'll use those as determining ratios and transforming from one unit to another. Okay, any issues on that, let me know. So just from what I was saying there, if you increase the vapor pressure, you need to increase the boiling point. And you have a look here, water at 760 degrees Celsius, 760 millimeters of mercury, or 760 torr, which is 1 atmosphere, 101.3 kPa. Water boils at 100. But what happens if we increase the pressure? So there's more pressure, more air pressure pushing down on that water. Okay, look, I need more energy, I need more fire, okay, to get that water boiling. And if we were at the top of Mount Everest, okay, I have no idea what the pressure is on the top of Mount Everest. That's a great one, though, for someone to Google and answer and email me. And somewhere in there, okay, the boiling point, if you were boiling water at the top of Mount Everest, would be in here somewhere. Okay, and you can see the same thing here. This works there. There's ethyl ether, there's ethyl alcohol. All works the same. Good. Sorry, I'm just kind of moving through. More so scared of my kids coming home and just tackling me or something like this. So we're moving. We still have a ways to go, so I'll probably break this up into a couple of videos. You guys can have a look at this. Won't have time, but it's straightforward. Changes of state. Okay, like here we're talking, let's just take water. And that's what the first 18 slides or 14 slides are all about. It's just water. Can have 3 states of matter. Well, actually there's 4, but we're only going to deal with 3 in this slide here. You've got solid, and just know there that ice can be below 0. Here I have temperature, okay, going from -20 to 120. Here I'm adding heat, I'm adding fire. Okay, so here I have a piece of ice at -20, and I'm adding heat to it, and you'll see there it's still ice, but at 0 degrees, it's weird. I'm not increasing temperature, but I'm increasing the fire. I'm adding heat, but the temperature isn't increasing. That's because we're in a transition phase here. We're moving from a solid to a liquid, okay? And it's almost like a popcorn effect. You'll know there that ice, the molecules aren't moving, they're vibrating. Okay, the kinetic molecular theory. And then at 0 degrees here, we keep adding heat, and those water molecules will start popcorn, and they'll explode off of the solid crystal ice mass, and you'll get this popcorn effect. And that's what's going on right here. And then at this stage here, there's no more solid ice left. It's completely liquid. And then we move on into the liquid phase. And you'll see there that this heat of fusion is replicated in so much the fact there that we're moving from a liquid to a gas here at 100 degrees. And you'll see the same kind of thing is happening. I'm adding more heat at 100 degrees, but the temperature is not increasing. Why? Popcorn. Okay, this here, it's moving from a liquid though into steam vapor molecules. This is called the heat of vaporization. I'm sure you guys have all heard it there before. Okay, great little multiple choice questions. Hydrogen bonding. Uh-oh, the beasts are home. Oh yeah. All right, I gotta pause it here. Okay, I'll another video.